So let's do the integral of the square root of x plus 1 over x. What we need to do is apply a rationalizing substitution. We can see that the integrand has a square root term, so this isn't a rational function. What we would like to do is turn this into a rational function using a u substitution, so that both the numerator and denominator of the fraction is a polynomial, which is what a rational function is. And of course, a rationalizing substitution is a u substitution where we turn a non-rational function integrand into one that is a rational function, which is easier to work with. So in order to do this, we should substitute u equals the square root of x plus 1, which means du is equal to 1 over 2 times the square root of x plus 1 dx. If we multiply both sides of the equation by 2 square root of x plus 1, we get the relation dx equals 2 times square root of x plus 1 du. And since we let u equal the square root of x plus 1, we can replace the square root of x plus 1 on the right-hand side of the equation with u, so this just becomes 2u du. So dx equals 2u du. We also need to find an expression for x in terms of u. Since u equals the square root of x plus 1, if we square both sides of the equation u equals the square root of x plus 1, we get u squared equals x plus 1. And if we subtract 1 from both sides of the equation, we just get x equals u squared minus 1 after switching the order of the equation. If we substitute all of this into the integral, the numerator becomes u, since we let u equal the square root of x plus 1, and the x in the denominator is replaced by u squared minus 1, since we worked out that x equals u squared minus 1, and dx is replaced by 2u du, since dx equals 2u du. We can simplify this expression and rewrite this as the integral of 2u squared over u squared minus 1 du, and we can also take out a constant multiple of 2 to the front of the integral. So this just becomes 2 times the integral of u squared over u squared minus 1 du. So now we have a rational function in the integrand, but we would like for this to be a proper rational function, which means the degree of the numerator needs to be strictly less than that of the denominator. The denominator is a quadratic, so we need the numerator to have a degree of 1 or less, and right now the numerator is a quadratic, so it's not a proper rational function. We could use polynomial long division to rewrite this as a sum of a polynomial and a proper rational function, but there's a simpler way to do this. What I'd like to do is rewrite the numerator as u squared minus 1 plus 1, and this is still divided by u squared minus 1. And this is still the same expression because all I've done is subtracted 1 then added 1 in the numerator. We can then split the fraction into 2 separate fractions, so this becomes 2 times the integral of u squared minus 1 over u squared minus 1 plus 1 over u squared minus 1 du. And all I've done is split the fraction into a sum of 2 fractions. This equals 2 times the integral of 1, since u squared minus 1 over u squared minus 1 is just 1, and the plus 1 over u squared minus 1 stays the same. If we factor the denominator of the rational function, the fraction becomes 1 over u plus 1 times u minus 1. And the next thing we need to do is to use partial fractions to split the fraction into a sum of 2 smaller fractions. So since the denominator is a product of the 2 linear factors u plus 1 and u minus 1, we would like to rewrite the rational function in the form a over u plus 1 plus b over u minus 1, where a and b are constants. That's how we do partial fractions when we have distinct linear factors in the denominator. We have to split the fraction into a sum of fractions where the denominators for each fraction correspond to each of the linear factors in the original rational function, and the numerators are all constant terms. So to determine how to rewrite the fraction in this form, we need to solve for the coefficients a and b. The first thing to do is to multiply both sides of the equation by u plus 1 times u minus 1, which gives us the equation 1 equals a times u minus 1 plus b times u plus 1. Since the equation is supposed to be true for all values of u, and we are trying to find which values of a and b will make this identity true, we can substitute with any value of u. So suppose we let u equal 1. This will make the entire a times u minus 1 term equal 0, so the entire term just disappears, which is useful for solving for the coefficients. So if we let u equal 1, then the equation becomes 1 equals a times 1 minus 1 plus b times 1 plus 1, and this just implies that 2b equals 1, so that means b equals 1/2. If we let u equal -1 and plug in the value of u into the equation, it becomes 1 equals a times -1 minus 1 plus b times -1 plus 1, and the entire term with the b coefficient just turns out to be 0 and disappears. So this becomes -2a equals 1, so a equals -1/2. Since we were trying to rewrite 1 over u plus 1 times u minus 1 in the form a over u plus 1 plus b over u minus 1, and we worked out that to make this equation true, we need a equals -1/2 and b equals 1/2. So we can rewrite 1 over u plus 1 times u minus 1 as -1/2 over u plus 1 plus 1/2 over u minus 1. And what I've done is just substituted the values of a and b into the right-hand side of this original equation. And we can simplify this expression further and just rewrite this as -1 over 2 times u plus 1 plus 1 over 2 times u minus 1. So since we worked out how we can rewrite 1 over u plus 1 times u minus 1 as a sum of smaller fractions, the expression becomes 2 times the integral of 1 minus 1 over 2 times u plus 1 plus 1 over 2 times u minus 1 du. So this is good because we can easily integrate each term separately. So this becomes 2 times u, since the integral of 1 is u, minus 1/2 times ln of the absolute value of u plus 1, which is the integral of this second term, and then plus 1/2 times ln of the absolute value of u minus 1, which is the integral of the third term, plus some constant c. If we distribute the 2 into the parentheses, this becomes 2u minus ln of the absolute value of u plus 1 plus ln of the absolute value of u minus 1 plus c. And recall how we substituted with u equals the square root of x plus 1. So if we substitute that back in for the u, this becomes 2 times the square root of x plus 1 minus ln of the square root of x plus 1 plus 1 plus ln of the absolute value of square root of x plus 1 minus 1 plus c. And notice how we don't need the absolute value around square root of x plus 1 plus 1 inside the logarithm because the expression is always positive, so the absolute value becomes redundant.